Good evening, ladies and gentlemen. My name is Tanya Reinhardt, and I'm the Science Centre Coordinator of the UKZN Science and Technology Education Centre. And on behalf of the UKZN's College of Agriculture, Engineering and Science, I would like to welcome everybody to our public evening lecture, What Do Scientists Do? Today's given me a great privilege to introduce our guest speaker before this evening. But before that, we have some house rules to do. Just make sure that you muted your microphone at the bottom left of your screen. The microphone should have a red line across. Also, please switch off your camera to save bandwidth. We will have a Q&A session after the talk, and you can either post the question in the chat if you like, or ask directly after the talk. I'm delighted to introduce our guest speaker for this evening, Professor ONISIMO MUTANGA. He's a Professor of Remote Sensing and South African Research Chair, or SACHE Chair, in Land Use. His expertise lies on resource modeling, pattern and condition analysis in the face of global and land use change. This includes the development of innovative remote sensing approaches for improved monitoring and management of various ecosystems. And I'll see that I haven't switched on my camera. Apologies for that. Focus areas include ecosystem services, quantification, forest fragmentation, disaster risk assessment, rangeland monitoring, as well as invasive species modeling, among others. Professor MUTANGA is B-rated by the NRF and has published more than 300 journal articles. And I remember seeing in the synopsis that it says it's over 12,000. That is actually over 13,000 citations now. I checked. He's an editor of some international journals and sits in various national and international boards. This year, he also won the NSTF, also referred as the Science Oscar Award, for developing research capacity through the use of remote sensing techniques to support land use management. The title of tonight's talk is Capturing the Anthropocene Dynamics from Above, Remote Sensing of Terrestrial Vegetation. And I'm going to leave the stage to Professor MUTANGA. Can you please stop sharing your slides? And Professor MUTANGA, if you can just start sharing your slides. And the stage is yours. Oni,
okay, good evening.
Okay, can you start?
Okay. Can you see my slide now?
Not as yet.
Not as yet.
Not as yet, no.
And now?
You know, this is no, still not. I see your face. Now it's starting. You started screen sharing. Okay, super. But you are in presentation mode, so we see your notes.
Am I in presentation mode?
Yeah, we see your notes. You know, this is typical. So we tested it before everything was all right, and then suddenly,
exactly.
as always, you know.
Can you see it now?
No, not as yet.
Okay, let me try again. Now it looks like I'm opening so many windows now. I can't see which is which now.
Oh, don't stress, don't stress.
Okay, can you see it now?
Oh, perfect. Yes.
It's fine now.
Yes.
Okay, thank you very much. Good evening, ladies and gentlemen, and thank you for attending my talk today. And thank you, Tanya, for the warm introduction. I'm just going to give a talk on the work that we do. Of course, I won't cover all the work that we are doing. I'll just pick examples from some of the projects that we've been working on. And the structure basically is I'll start with contextualizing the topic, just defining what we mean by the Anthropocene and its characteristics, and go into the main problems that are affecting humanity. Then I introduce the remote sensing concept, highlighting some of the few theoretical aspects. And then I will end with the application areas, because we've done a wide range of application areas, but my bias today will be towards vegetation, with a particular emphasis on rangelands, rangeland monitoring. Now, if you look at the problems that are facing humanity, we can classify them into natural and anthropogenic, but I'm more concerned with the anthropogenic factors. And these are the ones that have been coined by the Earth system scientists as the Anthropocene geological epoch. And this is an epoch where human-driven Earth system processes in the past 70 years are now so large that they've ended what we call the Holocene and ushered in a new Anthropocene epoch, which is mainly driven by human activities. So this Anthropocene epoch is actually driving profound changes into the structure and functioning of this Earth system itself. Of course, 70 years, when you're looking at geological epochs, it's a very small period. This epoch is actually in its infancy at the moment, but we can see a lot of changes that are happening as a result of that system changes that are occurring as a result of the Anthropocene. This is mainly characterized by climate change. There's evidence of atmospheric carbon dioxide levels and global annual temperatures, which have been increasing since the 1880s. And there are serious changes in rainfall patterns, frequency and intensity, drought events, El Nino events, which are impacting on terrestrial ecosystems. But this is also associated with serious land use mismanagement and also intensification of land use, population increases, and densification, especially in peri-urban areas, putting pressure on the resources. If you're looking in rangeland systems, we are witnessing a lot of overgrazing, which is affecting the productivity of the lands. Now, we have witnessed this exponential rise in carbon dioxide and temperature increases since the 1880s. What I'm more focusing on, if you look at the first graph on the left side, since 1980 up to the present moment, you can see a sharp increase in carbon dioxide and a sharp increase in temperature. In fact, if you look on the right side, you can say that in the past 4 years, carbon dioxide is actually crossed the 400 parts per million mark, which is unprecedented. Something is happening, and it's actually affecting humanity. If we look at the projections that are being done through climatic modeling, you find out that from 1950 to 2000, that's the actual historical data set that we have. But if you look at this graph, the projections are showing a steep increase in temperature if we are using the RCP 8.5 scenario. And with this one, it means if we do nothing, taking the status quo as it is, what we are doing right now, by 2100, we'll experience an increase of 4 degrees, which is very scary. But if we do something about it, promote the green economy, then the graph will taper down. And you can see the blue line there that will show that by 2100, there will be very small increase in temperature. So the ball is in our court to make sure that we do something about this climate change impact. And these projections are telling a sad story if we do not act now. Now, what are some of the problems that we are experiencing as a result of these changes that are happening within the terrestrial environment. On the left side there, you can see that there is kind of woody vegetation which is extending. It's an expansive area. It's a picture that I took in the Drakensberg. And that is indicating bramble, which is an invasive species. And this area used to be a grassland where, you know, animals would graze. But you can see this cow here is only grazing a portion which is about 3 meters from the road here, where I took the picture. That's the only that is remaining there. The rest, which has been invaded by this particular bramble species, is no longer productive, is no longer useful for the animals. It means we cannot use it for anything because of this invasion. If you look on the right side, that's Parthenium, which has invaded the whole of Eastern Africa, including our own South Africa, in northern Zululand. This is where I took this picture. And this one is seriously affecting the productivity of the land. It has got what we call allelopathic impacts, where areas where it invades, it will destroy the soil chemistry. And you have serious degradation of that particular land. So that land cannot be used for any production after the invasion. You can see some of the socioeconomic and ecological impacts of this Parthenium. Human health risks. If you touch it, then you have serious blisters. If animals graze on this, then they will have blisters on the mouth. You can see this, and it eventually affects the health of the animal, which will eventually die as a result of this. But also affects crop production. As I said earlier on, the allelopathic impact of this particular invasive species are very, very serious in terms of destroying the environment. Some of the effects, problems that we are facing, including overgrazing around waterholes and areas where there is dense animals. And as a result of this climate change, we have reduced production of reduced biomass, and that competition of very little resources and the animals that we have will result in this kind of degradation. And these are some of the pictures that I took in Kokstad and also in Okombe, in the Drakensberg, where there is now serious soil erosion as a result of the depletion of vegetation resources. Coming closer home, we've got problems that we are having as a result of this. The extreme flooding events that occurred last year. And from the research that has been done by a few scientists, I quote here Professor Grab and others from the University of Wits, they did an analysis from 1836 to 2022 of the flood chronology in KZN. And they concluded that this was the most catastrophic natural disaster yet to be recorded in KZN. And this is where we had about 400 millimeters of rain in 24 hours. And compared to the wettest month of February in KZN, which receives a total of 100 millimeters, you can see that there's a serious deviation in terms of the rainfall that occurred during that period. And we all know the impact of this particular flooding in KZN, with about 400 deaths and more than 4,000 homes destroyed. But you can see that there is an interconnection between the problems that we are facing with climate change. One of the issues that exacerbated this flooding was the occurrence of alien invasive plants in riparian areas and the areas that are close to those water channels. And because alien invasive plants, some of them, they've got very shallow roots, they can easily get uprooted by the water, and then they end up clogging the drainage patterns. And hence, we end up having those floods, which is different from the natural vegetation with very long, deeper roots and very strong roots that can actually hold the soil together and therefore reduces that problem of erosion. So there's a serious problem that we are having where reduction of vegetation or replacement of natural vegetation on one end will actually impact on soil erosion, will impact on flooding and exacerbate the impact even on the destruction of homes and infrastructure within particular areas. Now, I've provided this background not to scare you about some of the problems that we are facing, but it is the reality. Now, what do we do? What as scientists do to assist in solving some of these problems? That's when we come in with our Earth observation, which is also called remote sensing. Basically, in simple terms, you are obtaining information about an object without getting in contact with that particular object. So if you're taking a picture with your camera, you're actually doing remote sensing. If you're looking at an object with your own eyes, you're actually remotely sensing that particular object with your own eyes. So our eyes are sensors. So that's exactly the same as you see this satellite here. It has got sensors on it that can actually observe the surface. That's why it's called Earth observation. Now, what does it do? What is its role in the context of what I've been talking about? It assists in improving the sustainable management of resources through an evidence-based approach. Evidence-based approach in the sense that we are collecting information. It can be near real time, or it can be real-time information about that particular object, and we can actually monitor that information or that particular area over time or over minutes, and collect that particular information which we can analyze and inform management. We can map ecosystem properties and functions and infer ecosystem processes. For example, we can look at productivity patterns. We can look at changes in quality of vegetation, for example, for animal grazing using remote sensing. And what is important here is that we do it in a spatially explicit context, which means that over an area, we can cover every part of the ground. We'll have information about that particular attribute that we are actually mapping. So that is the difference that we have from kind of ground surveys where you go to specific points or specific points, areas, and collect information without that spatial context. It provides synoptic, spatially continuous data at various spatial and temporal scales. So depending on the sensors that you use, depending on the datasets that you use, you can actually do at various spatial scales and collect certain information. And it assists in understanding and mapping the spatial heterogeneity of the ecosystem services that are provided. And it monitors threats to ecosystem services, their resilience, and it can quantify the benefits of ecological restoration. If we do something about climate change, if there are changes in the environment, then using remote sensing, you can actually trace and track that there are indeed changes, and you can show that in form of maps that will show those particular changes. And hence, you can actually evaluate the benefits of the restoration that we have done. Assists in maximizing the conservation and improve people's perception on the value of ecosystem services, because people would want to know what is happening to an area, what is happening to their resource. If you provide them with that particular information, they can actually appreciate in terms of conserving that particular system, because they have information, they know what the benefits are. For example, if you tell the people that this particular species, tree species, will be very important for carbon sequestration, it will reduce the problems of climate change, therefore it needs to be preserved, and provide information, provide data sets on those quantified carbon sequestered by those that particular vegetation, people will then appreciate its importance. Vulnerability assessment to emerging threats. I've talked about flooding, I've talked about bush encroachment, droughts, pests and diseases that are associated with temperature increases. You can actually map and monitor the spread of pests and diseases within a particular environment as a result of some of these changes that are occurring. You can use remote sensing to do that. Now, just a brief history. It didn't start now. You can see that the first area photograph over Paris was obtained in 1858, and this was obtained from a balloon. Someone got into a balloon and then took some area photographs that we now analyze to understand some of the structural buildings in Paris. 1903, a guy, Julius Negrona, actually put cameras on pigeons, and they let the pigeons fly over an area and take photographs based on that. And you can see that this is a castle, European castle, that was actually taken using those pigeons. You can see the wings of the pigeons here on the right and on the left side. And this castle was actually obtained from that particular camera. That photography is part of a remote sensing. Of course, what we are doing is much more advanced than what was collected during that particular time. Now, just briefly on the theoretical aspect, we depend on what we call the electromagnetic spectrum in order to obtain the information about an object. And essentially, it's where we have electromagnetic waves that are categorized into their wavelength location, and they are measured in what we call micrometers or nanometers. And it's in a continuum of energy waves, which are of the same speed, because when we're talking of the same speed, it's the speed of light, and speed of light is actually constant, but they've got different wavelengths and frequency. So when you're categorizing these within the electromagnetic spectrum, you will see that if you're looking at cosmic rays, gamma rays, then we are looking at very small wavelengths, but very high frequency. If you go towards the right, then you have longer wavelengths, but low frequency. Now, the sensors that I've been talking about now, those satellites that have been thrown into space, or if you put sensors on balloons, or if you put sensors on drones, they actually capture within certain portions of the electromagnetic spectrum. And the most important one is the visible region, which is between 0.4 and 0.7 micrometers, or 400 to 700 nanometers. And this is region called visible because this is the only portion that we can see with our own eyes, human eyes. We can only see this narrow portion. The rest we can't see with our own eyes. You need certain sensors to capture that particular information. Now, the sensors that have been designed, they've been designed in such a way that they can capture in different portions of the electromagnetic spectrum. So we've got hyperspectral sensors, we've got the multispectral sensors. For example, Landsat TM will capture in the visible, the blue, green, red, near-infrared, thermo-infrared, and shortwave infrared. That's all. So you have bands within that particular region to capture the information. Now, when you're looking at an object, for example, vegetation, we have what you call a spectral profile. In other words, the vegetation will reflect radiation in different portions of the electromagnetic spectrum differently depending on the characteristic of that particular plant. So you see that if it's a certain species, it will have absorption features in the visible, which are mainly determined by the amount of chlorophyll or other pigments that are in that particular vegetation. And you see that in the near-infrared, because of the structure, canopy structure of that particular vegetation, it will reflect a lot of radiation, so the curve will go up because of what you call mount scattering effects. So the radiation is reflected a lot in this particular region. That's why our reflectance is very high. But as you move on, you also have other constituencies within the plant that absorb electromagnetic radiation, like leaf biochemicals, protein, lignin, cellulose. All those, they absorb radiation in specific portions of the electromagnetic spectrum. So the characteristic features of this profile will actually define the object that we are seeing on the ground. I could produce a number of spectral profile of other features. For example, if it's an urban area, or it's a soil, or it's water, it will actually have a different profile because it reflects differently based on its internal characteristics. So that's all the essence of remote sensing. Based on that concept, you can actually discriminate between those particular features based on their spectral characteristic. What you need to understand is, if you are looking at a particular component within that particular feature, then you have to have the scientific understanding of where within the electromagnetic spectrum does it absorb or reflect electromagnetic radiation? And that's based on that, you can actually focus on that particular aspect and you can map that particular feature. Now you can see that if I'm looking at this profile, I've got put an example of Landsat thematic map, mapper, which is a satellite that has been in existence for the past 40 years now. With its some had 7 and now we have got 8 bands. You can see that it has got bands in the blue region, the green, the red region, and the near-infrared, and part of the shortwave infrared regions. But you can see that there are gaps here. There's nothing, which means this particular sensor does not see anything between 850 and 1550 nanometers. There's no information that is contained there in that particular sensor. But there's information that is contained in part of the near-infrared and also the visible. This is compared to what we call the hyperspectral data. If you look at this vegetation profile, you can see that it's contiguous. There's no gap on this particular profile. Why? Because this hyperspectral sensor collects information in every band, in every portion of the electromagnetic spectrum between, say, 400 and 2,500 nanometers. It's got bandwidth of less than 2 nanometers. So every part will actually get information. So you end up having about 640 bands that you can analyze, which is completely different from a Landsat sensor, which is only 8 bands. And you can see that if I was to plot the bandwidth of hyperspectral, it won't even fit here. It's less than 2 nanometers, and it's very, very narrow. Whereas that for Landsat is very wide. This has got serious implications again for remote sensing. The wider the bands, the more the averaging of information. It means you may not capture some of the detail or subtle features of an object that you might be interested in. But if it's very narrow, it can capture detailed, very subtle information within a particular object, and you can actually isolate that particular feature within an object and map it using hyperspectral data. So there are various sensors that have got their own advantages and disadvantages. Depending on what you want to use it for, you have to make a selection, an informed selection of the sensors that you need to select for use. So if you're using hyperspectral data, you end up with what you call a hyperspectral cube, whereby you have a spectrum in each position of a large array of spatial positions, so that any one spectral wavelength can actually be used to make a recognizable image. So in this case here, if you look on the x-axis, this is one image, but if you look on the z-axis, these are several bands now that are actually capturing information within this particular area. If I look at one image only, this is one image that we took in the Kruger National Park, band 726. It's only one band that I'm representing here, which is showing an area in the Kruger National Park. But behind it, if we take all the bands that are within the electromagnetic spectrum, we end up having about 640 of them for one particular area. And this will now translate to what we call big data. It means it's multidimensional. It's a lot of big data set providing information over a small area that would need now a lot of computation, a lot of analysis to extract the relevant information that you are interested in. That's why we are exploiting a number of statistical approaches, a number of radiative transfer modeling approaches in order to extract the relevant information about that particular object that we are interested in. So this will show you the various bands about one particular site, which shows information for that particular area, and you can play around with those particular bands in order to enhance the image and extract the relevant information that you want. So it's not about only getting one band and then you analyze it and get a result. It's about a combination of several bands. It's about analysis of extracting information, data mining based on certain approaches, looking, for example, what you call the red edge shoulder, or looking at band depth of certain absorption features. you extract that information for the purpose of identifying that particular feature that you are interested in. That's the process, that's the whole process of remote sensing analysis that we actually do in order to get more information about an object. So as application examples, I'm done with the theoretical aspect now. In terms of application examples, some of the work that we've been doing is, for example, mapping biomass and nutrients in rangelands. Of course, these are very critical variables that helps in explaining animal distribution and in explaining the feeding patterns. And if you map the distribution of nutrients, map the distribution of biomass, palatable species in an area, then you can actually identify critical areas for conservation and restoration. For example, in the northern Kruger, there are certain areas called exotic sites which are very highly nutritious, and if you can actually map those sites, you can understand the distribution of animals, and you can actually isolate those areas for conservation. But you can also use it for determining burning regimes. You can see on the map on the left side here, this Kruger National Park, and there are points that are distributed across the whole park. It's about 18,000 square meters in size. And these are called, these are what you call the vegetation, VCA sites, vegetation condition assessment sites. And this is where the park managers, they actually collect information on vegetation every year in order to help them with management decisions. For example, in determining where to burn, prescribed burning in those particular areas. If they find out that an area is got about 4,000 kgs per hectare of grass biomass, then that area, they need to burn it. But now you see that these points are scattered. Of course, on a map, it appears as if they're dense, but there's a very huge distance between these particular points. So in terms of management decisions, yes, they might use this information, but it's not giving a whole picture. What about the areas that are in between? We don't have information on that. But now, when we map with remote sensing on the right side, you now have a complete coverage of that particular biomass in the whole of Kruger National Park, which means at every pixel or at every point that you can just click on, you'll get a biomass value. It's as a result of the mapping that we do with satellite image that will give this complete coverage. So when they now come to do their prescribed burning, they can now just do a polygon of areas that are above a certain level of biomass, and then that's the one that they can actually isolate for their prescribed burning, which is more accurate and more informative in terms of making management decisions. In terms of nutrient distribution, of course, as I indicated to you, that depending on the satellite sensors or the sensors that you use, there's certain information that you can actually extract about an object. And in this instance, if it's vegetation, if you're looking at foliar nitrogen within a plant, that's a very, very subtle object, a characteristic of that particular object that you need to very, very high resolution data sets in order to extract that. And in this case, we use hyperspectral data to detect and map foliar nitrogen concentration within particular grasslands. And again, this was done in the Kruger National Park. You can see that as evidence that our approach actually works very well. This is one of the experimental sites where ecologists actually partitioned the area into blocks, and one of them, they applied a certain burning regime, and another one, they didn't apply. And of course, this has got a serious implication on the nitrogen availability or quality of the grasses that you find as a result of the burning that they do. And we could actually pick the difference between those particular sites depending on the burning regimes that they applied. And we could show that there was high nitrogen concentration in another block as compared to the other one, which means it speaks to the ecological evidence that some of these remote sensing approaches that we do are very, very useful and accurate. Now, if I come to the Drakensberg area, where we have what we call the C3, C4 grass, which follow different photosynthetic pathways. This is a zone of transition, and there's been a lot of shifts in response to long-term changes in climatic variables, impact of temperature and carbon dioxide increases. It affects the C3 and C4 grasses differently. And these actually affect the forage quality of grazing animals. Of course, quality can be determined by the proportion of the palatable and unpalatable vegetation species in a rangeland, or you can actually do the actual mapping of the nutrient concentration within that particular field. And you could see that with the C3 and C4 variability, as they change as a result of climate change, you could see that there is also a change in the quality of the field. And that change actually disturbed the groundwater uptake, which has got an implication on biogeochemical cycling as well. So this is what some of the work that we did using satellite data sets to discriminate between those C3 and C4 grass species in the Drakensberg. And based on hyperspectral data set, we could see that the reflectance of different species that indicated the C3 and C4 is actually different. And this speaks to those chemical constituencies and physical characteristics that I talked about that will actually influence the reflectance in certain regions of the spectrum. If you look at an absorption feature, which is in a certain portion of the spectrum, you can see that this is one species, Eragrostis. The absorption feature is very, very deep as compared to Thymeda, where the absorption feature is actually a bit shallow. So we use techniques to extract the information about these particular features based on this absorption feature within the electromagnetic spectrum to characterize it. And then we can then map that particular species based on the information that we have obtained about that particular object. And this is what we call training of the images. So this is the distribution of the grass species that we could actually map using remote sensing data sets. We could actually track above ground biomass variation. We can actually track seasonality using remote sensing. If you look on the left side there, this is field data sets that we actually collect from February up to November. You can see the variability in terms of biomass from the actual field data that was measured. But if you look on the right side there, this is data set that was actually estimated from remote sensing. You can see very, very similar patterns with C3 grasses maintaining high grass biomass until around June, July, and then started dropping off. And our C4 grasses are dropping off earlier, which again speaks to the ecological concepts on the differences in between the C3 and C4 grasses in terms of when they actually start senescing and when they actually start reducing in terms of biomass and nutrient distribution. So our remote sensing actually could actually pick those variabilities. We could actually pick seasonality of various species based on that. And these are the maps that you can actually show based on that particular mapping that we do for various months. We could actually also confirm with some of the forage quality estimates that we made using remote sensing that they indeed explain the distribution of grazing animals, putting collars on the cattle. We could actually trace their movement patterns within a rangeland and see where they graze most of the time. And you could see that from this graph, they concentrate in certain specific areas. And from our remote sensing, when we overlay that concentration with the mapped remotely sensing data, we could see that the areas of high foliar nitrogen concentration are some of the areas where these animals were actually concentrating, which explains why they are distributed in those particular areas. Could also quantify productivity using remotely sensing data. Again, here we're looking at the restoration benefits that can be mapped using satellite data. And in this work, it was in Eastern Cape, where there is wattle, which is another invasive species, water invasion within a grassland ecosystem. And based on the satellite data that we analyzed, we could actually isolate those areas that had been rehabilitated versus areas that were still infested with wattle. And we could see that the variability in species richness between cleared and uninvaded areas was actually different. and we could actually map that using satellite data sets. Now, there has been a history of remote sensing satellite developments and sensor development over the years, which I've just explained as I was introducing the history of area photography. But you could see that within the electromagnetic spectrum, as I have alluded to, we've got different sensors that captures that. We've got our multispectral satellites, we've got our radar satellites, we've got hyperspectral sensors, we've got what we call the new generation multispectral sensors, which have got specific portions that they point to, which are critical for mapping some of the variables that we are interested in. And these new generation sensors, including our Sentinel-1 and Sentinel-2 data. And the beauty about it is that it's free and available. You can just need to download it on Google Earth Engine, and you can actually use it for mapping. And it contains very critical bands or portions of the electromagnetic spectrum that you can actually use to map your phenomena. We've got very high spatial resolution PlanetScope data, also freely available. Very, very high spatial resolution, which you can actually use to map certain features. For example, your informal settlements, you can actually use PlanetScope to do that. And we now have hyperspectral satellite data. The hyperspectral data that I was presenting was mainly obtained from either field spectroscopy or from airborne, where you have to commission a plane, mount a sensor on a plane, and then it goes to an area and takes images, and then you process that. But for the first time now, that's actually the second time, because we had Hyperion, which was not very useful. We have NMAP, which was commissioned in 2020 by the European Space Agency, and it's a satellite hyperspectral data set that you can actually obtain from that sensor. And based on the applications that you do to European Space Agency, they can actually collect information in your area of interest. So there have been developments over the years in terms of data availability, in terms of freely data that you can actually use for mapping purposes, which is different from the olden days where you had to cough out a lot of money. For example, with the hyperspectral, very expensive to commission and get it flown over an area. The beauty is that we have this long-term Landsat series since the 1970s, which is an archive of data which is available now for free, provided by the USGS, the government. You just download it from Google Engine, and this contains information for the past 40 years. And it means that you can actually track the changes that have been occurring in an area and map those changes and link them to some of the problems or some of the climate change events that were actually occurring in that particular area over a long period of time. Something that is unprecedented, something that we didn't have before, which is actually a very good advantage in science. We also have drone technology. This has been buzzing in the past 5 years. I think almost many organizations now have drones that they've acquired. We have also acquired a few drones that and sensors that we use for research purposes. The good thing about drones, yes, a drone is a drone that you can use to take pictures or to take images, but it depends on the type of sensor that you mount on it in order to get the relevant information that you are interested in. So it doesn't necessarily mean that every drone that you see there, you get the necessary remote sensing images that you are interested in. It depends on the sensor that is mounted on that particular drone. And we have acquired some multispectral sensors. We've acquired LiDAR sensors that we actually put on the drone in order to make some of the features. The beauty of drone imagery is that it is human control. You can actually take it the time that you want, any time that you want, which means if it's clear skies, nice weather patterns, then you can actually take out your drone and you can get the image that you are interested in. Offers more accurate and high resolution data because of the distance from the ground. that you can fly the drone. You can actually get very detailed information in terms of spatial resolution. You can even get about 2 centimeter resolution of data sets that you can use from a drone, which is different from those satellites which are about 700 kilometers away from the Earth. They are cost effective, and they've got a user-defined temporal and spatial resolution. Now, it's not only about remote sensing that we use. When you're doing our algorithm development, when you're doing our analysis and doing our modeling, we also combine that particular information with some of the ancillary data sets. It could be biophysical variables, it could be human-driven data sets that we can actually combine with the remotely sensed data in order to improve our prediction. So you have a solar radiation, your topography, your soils, land cover type. If you combine that within a particular model, you can actually do your predictions much better, because some of these variables on the ground are actually driven by these environmental factors. So that's the process of GIS analysis that we do with all these particular data sets. Now, this is the new generation data sets, sensors that I've been talking about. This is an example of worldview, which has got what you call a red edge band, something that is not available in satellite images like Landsat or Spot. And this is very critical, especially for vegetation mapping, because that's where you can see some of those constituencies that I was talking about, like your chlorophyll, like your nitrogen. You can actually map that using that particular red edge band, because it's sensitive to those variations. But it's not only about the images, it's also about the processing of the images, the extraction of the information from those particular images that we also need to develop, advance our knowledge on. And we've been leveraging on Google Earth Engine, which is cloud computing platform for extraction and analysis of this particular data set. The beauty about it is it doesn't require a lot of sophisticated computers or a lot of storage capacity on your normal desktop. It's on the cloud. So it means you can just work on the cloud. You don't have to worry about the processing power of your computer, or about the storage capacity of a computer, which is something that has helped, especially us here in Africa, because we don't have the necessary technology to get very high-powered computing to process some of these data sets. I've talked about 600 bands with a pixel resolution of about 2 meters. It means it's thousands and thousands of space that you would need in order to store or in order to manipulate that data. The more you start transforming that data into another form, you're already creating more data sets. It is very, very complicated, difficult. But the advances in technology have actually facilitated and allowed us to take advantage of the data sets that we have and process it within a cloud environment and get useful outputs out of that. But associated with that is also the advanced machine learning, artificial intelligence approaches that we actually use in order to extract that information from the satellite images for mapping purposes. Okay, this is my last slide now. What are the main highlights? Remote sensing can actually provide direct and surrogate information for various attributes within the environment. There are huge opportunities with freely available data with high resolution, with LiDAR, for example, Sentinel, radar data sets, Planescope, drones, and also the Landsat program, which has been in existence for more than 40 years now, is actually very, very useful for our monitoring purposes. Cloud computing, machine learning, and artificial intelligence. We are within the fourth industrial revolution, and we are taking advantage of those scientific developments in order to improve our mapping methods, mapping approaches. And so we are getting more and more accurate images and accurate products as a result of our processing and the availability of this technology that we take advantage on. But also another advantage that we are having is the open data policy. The world is opening up. We used to have serious problems getting information, getting satellite images It was only the military that had access to some of this information, but now it's open to the civilians, open to the public. We can actually take advantage of this and get that data set and use it for our mapping purposes to understand the Earth. What is important is, yes, we do the science, but we need to bridge the science action gap. If we just do the science and we don't translate it into into action, then it will remain in our libraries, it will remain in our published papers, but then it's not useful to humanity. So we try as much as possible to link up with various organizations, link up with various municipalities. For example, the Durban Research Action Partnership that the university is involved in, where we work with the municipality, eThekwini municipality, and we've got a lot of research that we are doing within that particular DIRA program, where we apply some of these technologies to assist in informing action on the ground on managing the environment. COGTA, we are involved with them in terms of flood risk assessment, flood risk mapping. That's also another example of where we are applying our knowledge and where we are applying our technologies to assist in solving some of the problems that the country is experiencing. Okay, I will end here. I hope I've not exceeded my 45 minutes.
No, you were absolutely spot on. Thank you very much, Ernie. Yeah, usually we have to kind of sometimes have to push people, but we have still time for questions. Please, okay, if people have a question, if you can just indicate, and then you unmute yourself and ask your question. Well, I don't see a hand coming up, so if nobody has a hand, I'll most certainly have a question. Oli, is there actually like a spectral database for plant species? So you were talking about that each plant has got like a unique kind of spectral pattern. So is there actually a database where scientists can go in and look up for look up these kinds of things?
It is not. When you're doing science, we kind of do it in bits and pieces. So there are some certain areas that they've got that profile of plant species, like in certain areas where we have been collecting data, we have those profiles. But there are some species where research has not been conducted in that particular area. You may not find actually that profile data. But let me hasten to say that there are certain areas that have got very advanced kind of information at the moment. For example, in the mining industry, where we have very known, well-defined spectral profile of certain minerals that are, that apply across the board. And of course, the advantage is that gold is gold. Whereas when you're dealing with vegetation, it varies according to various environments. We've got different species in different areas. That's why I said it's in bits and pieces. It's a bit challenging to get one consolidated database for that. But we do have some of that information for our own areas.
Okay, is there another question? If not, I'll have another one.
Yes.
Here we go. John Forbes, do you want to ask your question yourself?
Just to unmute myself there. Yeah, I just wondered if, you mentioned you're doing work with the eThekwini municipality. Are you identifying the areas of invasive aliens like Chromalina or Eupatorium, and how they are shifting over time?
Yeah, we have done some work on invasive species, but we didn't cover the whole of eThekwini. We have been doing like bracken fern mapping in the Western Durban. We also done some species mapping in some rural areas south of the eThekwini area. but we haven't really done a whole coverage of the province in order to see the shifting of those particular species. I think it's an area that we need to look into, which is very, very interesting. I think it's an area that we might discuss with the municipality in terms of the indicator species that are more critical, that we can actually try to focus on at a much more regional scale.
Thank you. Does it answer your question, John?
Thank you. Yeah, I think that basically does. Yeah, it's and as highlighted on the screen, you picked up certain areas of vegetation, and thinking of the Drakensberg, you got that Ohot, which although is indigenous, appears to be spreading.
Okay, right. Then Nomatile, you have a question. You want to ask the question, or do you want me to read the question?
Yes, great talk. Thank you very much. Question is based on there was a slide whereby you mentioned something about the use of remote sensing on biomass mapping and also nutrient mapping. So my question is, is there any acceptable threshold of biomass whereby you can then go for prescribed banning? Thank you.
Yeah, it depends. This one is an ecological question. From the experience that we have had, in the Kruger National Park, for example, they have got a threshold that they use for their prescribed banning. And if my memory serves me well, it's about 4,000 kgs per hectare. Anything that is above that, then they would ban. How they arrived at that particular figure, I'm not sure, but that's what they actually use. For us, we can actually map its variability, and we can actually link that to for the ecologists to look at the carrying capacity for animals, especially when it comes to grazing, similar to the quality, where we can actually map the foliar quality and link it to the species that are occurring within those particular areas. It will be an indicator that the area is actually degraded, or it's actually improving in terms of its productivity value based on that mapping.
Okay, thank you very much.
Okay, last two questions. Bruce, you gonna ask the question, please? And then we have Dr. Muporatsi, who can ask the question after you.
Thank you, Tanja. Thanks very much for a very nice lecture, Oni. I want to ask a question about looking at imagery very far back. As you mentioned, Google Earth Engine has quite access freely available to fine scale imagery. But if the further back you go, the more coarse the imagery is. Except that we have a really good database that can be scanned of aerial photographs that go back, in South Africa at least, to fairly the sort of 1930s and 1940s. Question to you, I don't know about, how easily accessible and how free is access to aerial photography that you might want to use for comparison far back?
Oh, that one is a challenging aspect. Even for us, when you're doing research, getting access to aerial photography is a bit of a challenge. It depends on the custodians. Of course, for us, we have been working with the municipalities. They've been providing us with some of the satellite images, of aerial photographs. But I have to admit that it's very difficult to get a whole coverage of aerial photography for the whole country. Of course, some areas are covered, but some is very, very difficult. And we have to note that aerial photograph has got some information, but that information is limited somehow, because we are dealing with just a panchromatic band here. It doesn't have all the information within the electromagnetic spectrum. So depending on what you want to investigate, of course, you can get those trends like wood cover change over areas. You can actually see that using aerial photograph. But if you want to go into details, then you may not be in a position to see that. But yeah, to answer, coming back to your question, it's quite challenging to get that.
Okay. Thank you. Dr. Muparatsi, do you want to quickly ask your question?
Thank you. Yes, my question is a simple one. I liked the what the professor mentioned about the aggressive invasion of bramble, Parthenium, and I have just referred to water hyacinth. I think that's the correct way to pronounce it. That's invading water bodies in Zimbabwe. And I find this to be quite scary. And given the reality around this aggressive invasion, by these plans, what solutions have we developed to deal with, the possible risks that we may end up possibly without grazing land and with, without reliable, water sources within our biosystems?
Yeah, of course, there are quite a number of intervention measures that various organizations are doing. For example, the Umgugungi of municipality has been on a drive to remove alien invasive species in rural areas. Working for water, they've been quite involved in the removal of alien invasive species. It is a challenge. I must admit that. The government is facing a serious challenge here with these invasive species. On one hand, it's very, very costly to remove the invasive species, and there are various control measures, including biological control measures, including mechanical control measures that they do, like uprooting and stuff. But it's also very labor intensive. It's labor demanding. You need a lot of people to go into those areas and remove alien species. And removing it does not necessarily mean that it doesn't come back again. In some areas, you remove it this year, the following year it comes back again. So it's quite a challenge, but we have to soldier on and keep on developing approaches that we can use to get rid of these alien invasive species. Otherwise, they are eating into most of the productive land and affecting the rangelands, grazing areas within the ecosystems that they invade. So it's actually a problem, but government is aware of that. Various organizations are aware of that, and they are doing some intervention measures to control it. Our job is to map, provide the information of where it is and how much it is and what it is, and then they can actually take action. Thank you.
Thank you, Professor.
Okay, thank you so much, everybody. Our time is unfortunately up, and this was our last look behind the scene talk for this year. And I would like to take the opportunity to say thank you to a number of people. To Dr. Sally Frost, my boss, who coordinated the event and who also publicizes the event, and Christine Kuhner, who filled in as a technical host today. Aso Grach, who designed the invitations and the wonderful backgrounds, and the countless people in the back who helped spreading the message. And last but not least, to our scientists who presented this year. So we had Dr. Ivory who talked about bioinformatics and HIV research, Professor Hussein Shemelis, who enlightened us about millets in 2023, Professor Caroline Moodley, who took us to the stars and talked about the Hyrax telescope, Professor Ursula Schala, who let us look beyond the individual, embracing system thinking and nature and the socioeconomics. And of course, tonight's speaker, Professor ONISIMO MUTANGA, who gave us a fascinating insight on how to capture the Anthropocene dynamics from above. You can also, if you've missed any of these lectures and you're interested in past lectures, please visit us on our website. You can go either to the Science Center website, STEC at UKZN, or you can go to the College of Agriculture, Engineering and Science website, where we have these links to these talks. I wish everybody a peaceful festive season and a prosperous 2024. And don't forget, What Do Scientists Do will be back in 2024. And now, please, if you can just unmute yourself and put your hands together for Professor ONISIMO MUTANGA. Thank you so much for this fascinating talk. Thank you so much. And good night, everybody. And as I said, have a wonderful 2024 and festive season. Goodbye.